Hi and welcome to the second video on forces from the Year 2 Mechanics content. And what we're going to be doing is having a look at when things are on inclined planes, so things on objects on slopes. In Year 1 it was all on horizontal or perpendicular. We're now talking about slopes because what we're going to be dealing with is having to split forces into different components, and that happens when you've got things resting on surfaces that are not horizontal. So here we go. Let's have a look at a book. And there's our book that we had from the previous video, sitting on a slope. So we've got the reaction force there, which is perpendicular to the surface of the slope. But then we've got the weight, the force due to gravity, which is still acting vertically. Now, in order to make the calculations easier, it's far easier to actually work with components that are parallel to the slope. You can see the green arrow put in there, so force is going in that direction. And then also perpendicular to the slope, which is forces going in that direction. Ooh, that direction there. Excuse my wobbly mouse work. Right, so what we need to do is have a think a little bit, particularly about how this affects our force due to gravity, our weight. Because this force here is not acting in one of our directions. So part of this force here is going to be acting to make the book try and move down the slope. So it's going to be part of it acting in that direction. And also part of it is acting as a counterbalance to the reaction force, so part of it is going in this direction as well. So we need to be able to split it. To be able to do that, we're going to need to do a little bit of work on the angles that we've got going on here. So we'll start off by thinking about that angle that's just appeared in red here. Clearly, if the angle between the slope and the horizontal is theta, that means that one there is going to be 90 minus theta. And then the angle that I'm actually interested in is this one under here. You can see this one here. And if I've got a right angle there, and this angle is 90 minus theta, it means this angle here, where my mouse is going to have to be theta. So as it turns out, the angle that I'm interested in is always going to be the same as the angle between the horizontal and the slope. Now that we've got that angle, we need to think about how much of this force is acting in each direction, and the way to think about it, again, as we saw in the previous videos, the force is always going to be the hypotenuse of a right angle triangle. So let's just have a look initially about how our weight is going to act parallel to the slope. And that direction is that one there. And putting that arrow in there helps us see the right angle triangle, which is here. Okay, and we've got a right angle at this point here. So this side here, which is the force down the slope, is opposite to the angle that we're interested in. So what we've got there is mg sine theta. Now, how much of that is going perpendicular to the slope? Well, that is going to be the other side of our right angle triangle, so that bit there. And because that's the adjacent side, that's going to be mg cos theta. So what we're going to do, every time you get one of these, you're going to get very used to splitting, kind of putting in the weight. And then I would always recommend drawing in this dashed line here as our perpendicular direction, and then kind of thinking very carefully about this right angle triangle that's going on underneath the slope there. Right, so let's have a look. We've got an example here with a book of mass 2 kilograms resting on a school desk. When the student opens the lid, we've got a frictional force holding the book in place, but how far can the desk be opened before the book starts to move? So, as it's mechanics, it's always start off with the forces diagram. Reaction force, force due to gravity, and we've got that 7 Newton force that's acting up the slope because the book is going to want to move down the slope, so that means there's a force acting up against up that's stopping it doing that. And the other thing I'm going to put into my diagram is that dashed line, just to indicate kind of the direction of that perpendicular direction to the slope, because that's going to help me think about what's going on with this force under here. So we know the book is going to move when the force parallel to the slope becomes greater than 7 newtons, and the only forces parallel to the slope are going to be the 7 Newton force here. Reaction force is perpendicular, that won't have an impact, so the other force has got to come from the force due to gravity. So we are looking at that force there. And this is my notation here for saying I'm going to resolve parallel to the slope. So what we've got is, in order for it to move, this force here, 2g sine theta, has got to be greater than the 7 newtons. Take the 2g now over to the side, and so we've got 7 over 2 times 9.8, and it turns out that's 5 over 14. So therefore, we've got a value for theta that is 20.9. So in order for this book to slide off the desk, the desk got to be open to more than 20.9 degrees. Okay, so moving on, let's add an extra question into this one. So if the book is 60 centimetres from the edge of the desk and it's open to an angle of 30 degrees, how long does the student have to react before the book falls off the desk? Right, so what we need to do is we need to think about the forces, and we need to think about how that book is going to move. And so the way to go about that is to think about acceleration, and we're going to get that from force equals mass times acceleration. So what I'm going to do is just recalculate things now that we've got this different value for the angle. So the angle is 30 degrees. So my force is going to be 2g sine 30 minus 7 equals mass times acceleration. So what I've done here, rather than here just putting the kind of the two forces comparing with each other, what I've done on this one is gone for force equals mass times acceleration. So there's my force down the slope. There's the force going up the slope in the opposite direction, so that's why it's a minus. And I've chosen down the slope to be my positive direction because that's where the book is going to accelerate. So now all I've got to do is divide by 2, and so this book is going to accelerate at 1.4 meters per second squared. So now what we're going to do is we're going to jump into a bit of SUVAT. Notice 60 centimeters. So that's got to be written as 0.6 because our standard SI unit is meters, not centimeters. U is 0. V we're not worried about. A we know is accelerating. And T, that's the thing we're trying to find how long it's going to take before it falls off the edge of the desk. Right, so S equals UT plus half AT squared. That's the thing that's going to allow us to find T. Plug in the values, and so we end up with T equals 0.926 seconds. So we've got that long to react before the book falls off the desk. Having said that, I will just add into this one the fact that this is a mathematical model, it's a mechanics model, so we are modelling everything, particularly the book, as particles. So you could criticise this model, say, well, you know what, it depends. If it's the front edge of the book that's 60 centimetres of the desk, the book has got actual size, so it might have a little bit longer until it actually falls off the desk. So we've got a little bit more reaction time than possibly the model might indicate. So again, with a lot of these models, you might get asked questions about how the model could be improved or how it might be inaccurate, or you might be asked to criticise it in some way. So just thinking about the difference between a mathematical model and the actual real life version. Okay, moving on. So here we go. Another example. We've got a child on a sledge, and it's on a slope, being held on a slope by a horizontal force. And so there's a few other extra bits and pieces in here that are well worth spending our time looking at. So here we go with our diagram again. So there's our sledge. And it's got the child and sledge have got total mass. We'll just call that M for now. We've got a reaction force there. We've got a force due to gravity there. And we've got this horizontal force, which I'm going to call X, that is holding the sledge in place on the slope. And then the final thing I'm going to put in there again is my dash line and my angle underneath the slope, because I know I'm going to need that later on. Right, key thing to think about here is this horizontal force here. Because it's neither parallel nor perpendicular to the slope, it's going in a slightly different direction, so it's going to have components in both directions, so we've got to think carefully about how we use that force when we start resolving it in our two components. So what I've done is just put this little kind of red dashed line in there just to help me think a little bit, because what I'm interested in is this angle between X and the slope, and hopefully we can see what we've got is a good old-fashioned Z angle from back in the day, or an alternate angle. If you remember back to GCSE, so that angle there is going to also be the same as the angle between the slope and the horizontal. Right, now we've got all that sorted, let's do a bit of resolving and see what happens. So let's first of all resolve perpendicular to the slope. So we're going to be resolving in this direction here. So we've got upwards, we've got R. Now, this thing is not jumping off the slope, it's not sinking through the slope, so whatever forces are going upwards have got to be matched by the forces that are going downwards. And clearly we've got the force going downwards due to gravity, and so that's going to be mg cos alpha. And also if we think about this force here, this force is almost acting as if it's pushing the box into the slope. If you just imagine taking that diagram and rotating it so the green line is on the horizontal, so if we just rotate it 30 degrees clockwise, you'll see that arrow here, this X arrow now appears to be pushing downwards. So that's why it's going in the opposite direction to the reaction force, and so it's going to be that bit there, and that's going to be X sine alpha. Now, we haven't been told the size of the angle, but we have up here got sine alpha is 3/5. So what that allows us to do is work out cos alpha and tan alpha as well. And my best way of doing that is I like to draw a little triangle. So I'll come off to the right hand side of the page, do a little bit of scribbling. So opposite over hypotenuse, 3/5, which means Pythagorean triple. That side there has got to be a 4, which that means that cos alpha is 4/5. So if we now put those values into our equation here, that's 4/5, that thing there is 3/5, and so that's what we've got. Now, we need to find the reaction force, and at the moment we've got it in terms of x, which is this horizontal force, so let's see if we can do something about that. So what I'm going to do now is resolve parallel to the slope and see if that allows me to work out x. So, what we're going parallel to the slope, so we've got in that direction there, and again it's being held in equilibrium on the slope, it's not moving, so we can put forces up the slope on the one side, so there's x cos alpha, and that's got to be equal to the forces going down the slope, which have got to be coming from gravity, which is going to be mg sine alpha. Now, what we can do is make this say x equals, so let's move the cos over, and sine over cos is tan, so we can write that as mg tan alpha, and let's come back over to our triangle over here, and we can see that tan alpha is 3/4, so we've got x is 3/4 mg. So now effectively what I've done is worked out the size of angle x in terms of m, the mass of the sledge. So let's now put that back into our equation up here. So from that one we've got 4/5 mg plus 3/5 times 3/4 mg, and as it turns out, you've got everything now in terms of mg. 4/5 plus 3/5 times 3/4 turns out to be 5/4 mg. And there we go. There is the size of your reaction force.